How does material creep cause structural disasters? Imagine a bridge that looks perfectly fine but is secretly weakening over time. That slow, hidden process is what we call material creep, and it can lead to serious structural failures. Creep happens when a material is under constant stress, especially at high temperatures over a long period. It's not a sudden event but a gradual deformation that slowly wears down the material's strength. Think of it like a piece of chewing gum stretching slowly when pulled. At first, it stretches easily, then it stretches at a steady rate, and finally, it might suddenly snap. This process has 3 stages. The first is primary creep, where deformation happens quickly but slows down as the material hardens. The second is secondary creep, which is a steady, predictable stretch that lasts the longest. The third is tertiary creep, where deformation speeds up rapidly, leading to cracks and eventual rupture. The main cause of creep is the movement of atoms within the material's structure. When materials are exposed to high temperatures, atoms can move more easily. In metals, grains slide past each other, and in polymers, chains slip and stretch. This atomic movement causes the material to stretch permanently, even if the load is below the point where it would normally break. Over time, this tiny deformation adds up, weakening the material until it can no longer support the load. Real-world structures like bridges, pipelines, or power plant parts, creep can be a silent threat. For example, a steam pipe in a power plant might look fine for years, but inside, creep can cause the pipe wall to thin gradually. Eventually, the pipe becomes too weak to contain the pressure, leading to a sudden burst. Similarly, turbine blades in jet engines are exposed to high heat and stress. Over time, creep can deform these blades, changing their shape and causing engine failure. Materials with smaller grain sizes tend to creep more because they have more grain boundaries where atomic movement can happen. Engineers often choose materials with larger grains for high-temperature parts to improve their resistance to creep. Changes in the material's microstructure, like the breakdown of carbides in steel or formation of graphite, can also weaken the material further. Creep is not just a problem for metals. Polymers and soft metals like lead can creep even at room temperature. Hard metals like steel need higher temperatures for creep to occur, but it's still a factor in many applications. That's why engineers must consider creep when designing everything from plastic pipes to aircraft parts. To prevent disasters caused by creep, engineers follow strict codes and standards that predict how long a component can safely operate under certain conditions. Regular inspections look for signs of deformation or microstructural damage. Advanced computer models can simulate creep behavior, helping designers choose the right materials and plan maintenance before failure happens. Learning from failures caused by creep teaches us that slow, unseen processes can cause sudden breakdowns. It reminds us that not all failures happen quickly or visibly. Sometimes, the damage is happening quietly over many years until it reaches a breaking point. Recognizing these signs and understanding how materials behave helps us build safer, longer-lasting structures. By studying real-world cases, we see how important it is to select the right materials, monitor their condition, and plan for maintenance. This knowledge helps us avoid future disasters and keeps the world around us safer and more reliable.